finding a needle in a haystack, a novel log analysis method will test clustering in distributed systems. Abstract. As the diversity and the complexity in digital design increases, the cost of the design verification also increases. In such a trend, verification engineers are struggling with the repetitive and tedious process, such as debugging common errors from different test cases. To solve this problem, verification engineers can use their own domain knowledge to prioritize test cases and find different errors. However, it takes time and effort to do it manually. And it also not so easy task to understand different designs and test benches with limited time and resources. In this paper, we propose another approach of a test cases prioritization algorithms based on clustering. Components from terabytes of simulation logs are considered as features in clustering algorithms. After clustering, the proposed algorithm reorders test cases with priority and recommends test cases that allows verification engineers to achieve a specific rate of errors detection as early as possible. We also propose robust and scalable system architecture that can handle terabytes of data for practical use in design verification industry. Introduction. As demand on digital design increases across industries such as smartphone, wearable devices, and automotive, engineers are required to design more diverse and complex digital logics. Development period is also getting shorter, with shorter release cycles of finished product. In such a trend, conventional development methods in digital design and verification have their limitation to its sustainability, scalability, and usability. These limitations give digital design engineers missions to innovate development process by integrating software technologies such as machine learning and big data in hardware industry. One of the important missions is to reduce debugging efforts in design verification. The process of the design verification accounts for approximately 70% of the entire process. There have been many efforts to reduce cost for design verification. However, verification engineers are still struggling with the tedious tasks such as debugging common errors from different test cases or finding critical errors in the later stage of development process. In this paper, we propose a novel approach of a test case prior prioritization (TCP) algorithm with clustering to reduce time and expenses in debugging process. The proposed algorithm prioritizes test cases based on clustering result. Clustering algorithms are unsupervised machine learning techniques to find clusters having common features, and this paper uses components as features for clustering algorithms. The components are extracted from terabytes of simulation logs and provide information about what actions are taken while running simulation. Based on component test cases are clusters with our other similar test cases, and then test cases are prioritized in each cluster. The contribution of this paper include clustering algorithms based on component from logs, test cases prioritization algorithms in clusters, system architecture for machine learning application. First, we propose a clustering algorithm based on component from logs. Components include functions such as a task, class, and sequence, and errors such as UVM errors and user-defined errors. Clustering algorithms consider these components as features for clustering, and each component is given weight for better clustering result depending on the maturity of verification. By applying different weights on specific component, clustering is extended to prioritize more important components to find critical errors first. Second, we propose test case prioritization algorithms. The algorithm prioritizes test cases based on how different types of errors can be found as early as possible. In the conventional debugging process, verification engineers depended on their domain knowledge of design to prioritize test cases, and this was tedious task. For instance, debugging common errors in different test cases, the proposed algorithm prioritizes test cases and gives a higher priority to test cases and with more uncommon errors and shorter runtime. In algorithm section, 5 different algorithms are described, and in a result section, they are compared to determine which algorithm is appropriate to reach a target rate of error detection as early as possible. Finally, we propose a robust and scalable system architecture for machine learning application in the industry. The proposed system architecture is sustainable, scalable, and reusable. It enables machine learning models to be serviced in the production level and updated with new data sources. The system is also scalable in that it is composed of distributed servers and databases, and only one machine learning model is loaded regardless of the number of inference requests. Each machine learning pipeline is reusable and a process of continuous integration and development of the proposed algorithm. Section 2 is background. Clustering algorithm. K-means clustering algorithm is one of the most widely used clustering algorithms. This algorithm initially selects k-point for centroids of clusters randomly. It computes the sum of the squared distance between point and all centroid, and then assigns the closest cluster. This process is iterated until there is no change in the centroid. Density-based spatial clustering of application with noise (DVCON) algorithm is used to find clusters considering density, and it is useful when the number of clusters is not specified. DVCON algorithm uses two hyperparameters, epsilon and mean PTS, denoting distance and minimum number of clusters respectively. Ordering points to identify the cluster structure. OPTICS algorithm is used only with mean PTS without epsilon and it is better suited for uses on large datasets than DB-scan. This paper focuses on K-means algorithm, which is suitable for the service system in real time and characteristics of data. A weighted clustering algorithm is one way to improve clustering algorithm for status of verification progress by giving weight to specific features. In the simple K-means algorithms, each feature contributes equally to clustering, and it makes algorithm concentrate on finding the optimal way to separate different features based on similarity. On the other hand, by giving specific features more weight, a weighted clustering algorithm can improve cohesion of clustering co- cohesion of clusters, and it is consequently useful when finding critical errors or prioritizing important features. In this paper, we use K-means clustering algorithms because it is suitable for our dataset and our parallel system. To find the optimal K-value in K-means clustering algorithms, each cluster is evaluated with silhouette scores and elbow method. Silhouette score and indicate how clusters are well apart from each other and how similar an object is is to its own cluster. Elbow method finds optimal K-value until there is no remarkable improvement even with additional cost. In this paper, we compare a K-means clustering algorithm with and without weights and set K-value that maximizes silhouette score considering slope in elbow method graph. Test case prioritization. There has been a variety of research on test case prioritization. B. Miranda proposed a function analysis system test technique FAST approaches to scalable similarity-based test case prioritization by using mean hashing and locality-sensitive hashing algorithm for finding test cases with a big data set. A. Wahba, and J. O'Neill Lane and F. Rahman proposed a tool with machine learning techniques to detect failures and associated with the actual bugs in register transfer level in x86 processors. So test cases prioritization is a main issue in the software industry as well. Fang, C. et al. Proposed a similarity-based test case prioritization using ordering sequences of program entities. They analyzed the open source project as a target. T. B. Duer and H. Hamatin proposed a similarity-based approach using historical failure data based on a class metric that estimates test cases quality. Daniel Fletcher et al. Studies test prioritization based on a similarity-based reuse of test codes. In this paper, we use a similarity-based approach, the same method in the related work. However, we focus on the prioritization with the clustering algorithm and consider not only result of the test case simulation, but also a component of the test cases. System architecture. System architecture is of large importance of deploying successful machine learning models. Even if a good machine learning model is developed, it is of no use when the model remains in local environment. Moreover, if the development and deployment process is not automated, machine learning models would be hard to be updated with a continuous stream of data in design verification process. In this paper, we introduce robust and scalable architecture for practical use of the machine learning models in design verification. The system includes in-memory machine learning models, distributed systems, and automated pipelines. First, the concept of the in-memory machine learning is a method to speed up model inference time by loading machine learning models in memory, not disk. In-memory machine learning is a key for real-time inference. The in-memory approach is used in other data processing domains. For instance, Spark on an open source for distributed system reduces data processing times much more than Hadoop, well-known distributed file system, by using in-memory approach. Second, distributed systems also improve data analyzing and processing speed. Clustering algorithms such as K-means clustering are appropriate machine learning algorithms for parallel processing in distributed systems. In addition, as log data processing can be performed independently, distributed systems are efficient for handling terabytes of simulation logs in parallel. Such architecture maximizes the performance of processing a large dataset. Finally, automated pipelines enables the system to position in design verification process. In our previous work, we proposed a design verification automation system. In this paper, the proposed system architecture is based on the previous system with the newly added automated data analysis and machine learning pipelines. In the automated pipelines, for example, the system automatically cleanses data, finds optimal hyperparameters such as the number of the clusters K in K-means clustering algorithm, and deploy models in the automation system. Airflow, an open source to automate workflow, is used for the system. The section 3, algorithms. The goal of the proposed algorithm is to reduce time and cost to find errors in test cases with minimum number of regression and least resources. The algorithm is composed of three phases: data pre-processing phase, and clustering phase, and the test case prioritization phase. In the data pre-processing phase, duplicate components are removed, and the preserved components are transformed into vectors for clustering algorithms. In addition, to maximize the accuracy of clustering algorithms, the number of features is reduced by dimensionality reduction algorithms. In the clustering phase, test cases are clustered based on components extracted from simulation logs. Components are considered as features for clustering algorithm. For a weighted clustering algorithm, weights can be given by a specific component based on engineer's domain knowledge or the importance of components. In the test case prioritization phase, test cases are prioritized in each cluster through of the five algorithms. The purpose of this phase is to sample representative test cases to find different errors as early as possible without learning all test cases. Each TCP algorithm is chosen depending on the circumstances of verification. The overall of the flow in the algorithm is shown in figure 1. Flow of the proposed algorithm. Data processing pre-processing phase. In the pre-processing phase, components are pre-processed prior to be used features for clustering algorithms. First, duplicate components are removed and the preserved components are tokenized. Second, tokenized components are vectorized with the term frequency and inverse document frequency (TF-IDF) vectorization. A method to vectorize words considering the impact of the words to be documented. Finally, dimensionality is reduced by using principal component analysis (PCA) or singular value decomposition (SVD). So PCA finds orthogonal basis to reduce dimensionality while preserving variance of the original data, and the SVD decomposes complex matrix into singular vectors to reduce dimensionality. For example, the number of dimensions decreases to 92% and 85% based on PCA and SVD, respectively, from our data set. Figure 2 shows comparison result between without dimensionality reduction with the dimensionality reduction method. Considering all components of as 3,990 features, the dimensionality reduction method helps clusters separate from other clusters compared to the method without reduction. Figure 2, A. Comparison, inertia, and silhouette score. B. t-SNE, result of K-means clustering without dimensionality reduction and the reduction without dimensionality reduction and dimensionality reduction. C. Principal component analysis (PCA) and D. Singular value decomposition. The clustering phase. In the clustering phase, to find the optimal K value in the K-means clustering algorithm, silhouette score and elbow method are used. In our automated system, an optimal K value is automatically given based on maximum silhouette scores. Figure 3b describes how to select the largest silhouette score between 0 and 30 of the K value. The K value above 30 is considered as meaningless based on elbow method. At first, to ensure the components are valued enough as features as a naive clustering and the proposed component-based clustering method are compared. The naive method extracts components from test names, which contain intuitive clues about test cases. The component-based clustering method, however, extracts components from log files. Both methods vectorize components with TF-IDF, the number of word occurrences in each document. Figure 3 shows result of comparing naive method and component-based method. The points in clustering figure 3a are much sparser than figure C2, and meaning components have more abundant information as features for clustering together tightly. Figure 3, t-SNE result of K-means clustered by test name using PCA, comparison inertia, and silhouette score. For weighted clustering, it gives different weights to each component. Each component is not considered equally as it is the simple clustering algorithm. For example, common and minor components can have a smaller weight, although some critical errors can have larger weight. As components are divided in two types, one, non-error type such as a task, function, or sequence of test cases, and error two, error type included tool errors and user-defined errors. The reason for such a separation is to consider errors and non-errors differently on a user level. This means that users sometimes consider errors more importantly, or sometimes consider non-errors more importantly. By giving different weights on non-errors and errors, clustering algorithms can be customized depending on different situations. Based on how much weight each component is given, clusters are reorganized. The equation of obtaining weight value is as follows. Specifically, alpha is a hyperparameter that denotes how much weight is given to all components. Beta is a higher hyperparameter that denotes how much weight is given to all errors. W is a hyperparameter that denotes how much weight is given individual component and error. The matrices of weights WC and WE are multiplied to TF-IDF value of individual component and errors. Figure 4a showed the result of K-means clustering without weights, and figure 4b showed the result of K-means clustering with weights and specific errors related to access register. Hyperparameters were set to give more weight on beta than alpha, and each W was given equally except the specific errors. These hyperparameters setting the mean test cases are clusters more considering on a specific errors. Figure 4b shows the average distance between points from the centroid is smaller than figure 4a, and because the specific errors are significant component for clustering. Figure 4, t-SNE result of K-means clusters, and B, t-SNE result of weighted K-means clustering. Test cases prioritization phase. To find the appropriate algorithm in test case prioritization. 5 algorithms are compared in this paper: without TCP, 1 without TCP, 2 random, 3 farthest first, 4 closest first, 5 error count and runtime wise. Without TCP has nothing to do with clustering. It's a way of running regression in the original system. Random algorithm samples a specific number of test cases randomly from clusters. Farthest-First is an algorithm selecting test cases in the order of the farthest distance from the centroid of each cluster. Closest-First is an algorithm selecting test cases in the order of the closest distance from the centroid of each cluster. Error count per runtime wise is a prioritization algorithm that considers the number of errors in a test case and each runtime. This algorithm is based on the hypothesis that when there are many error types in a test case, the test case is highly possible to be useful when extracting more possible failure cases, and when the test case has shorter runtime. Other test cases will learn and find other errors as early as possible. So, of all 5 algorithms, depending on different environment, one algorithm is selected based on the result of how early a specific rate of error detection is achieved. Based on the selected algorithms of the five candidates, the test case prioritization algorithm reorders of the order of regression. For each cluster, the five highest prioritized test cases are selected and simulated. The process of selecting the test cases and regression is repeated until all errors are detected. The detailed algorithm is described as follows. Algorithm: the test case prioritization from the clusters. Chapter 4 Architecture. This section introduces system architecture of the proposed system. The overall architecture is shown in Figure 5. While running a regression automation pipeline runs the design verification automation steps such as environment setup, compiler simulation. The simulation data is stored in distributed databases and file systems for efficient access to databases. After regression is finished, machine learning is pipeline executed. In the pipeline, log files are processed by distributed computer servers, and proposed algorithm prioritize the test cases based on the clustering algorithm. Next, the machine learning model is deployed to the web server and loaded in its memory, and this system architecture enables proposed algorithm to be updated in the verification automation flow. In this section, it is discussed how each part of the system contribute to the practical use of machine learning in the design verification process. Figure 5. Overall architecture of the proposed system. In-memory machine learning model. In-memory machine learning model is literally a machine learning model that is loaded on the memory, not disk. As the memory access is much faster than disk access, this method takes advantage of faster model inference time. This method is combined with software technologies such as web server and design patterns. For web server, the system of the engines, uh, an event-driven web server, Kunikon, a web server gateway interface, and Django, one of the most widely used web frameworks in Python. Engines is used for load balancing and caching, and it decreases response time and reduces overhead to worker thread. In the experiment, model inference time took average of 20 to 40 seconds, and most when a job is queued by workload balanced platforms such as your load sharing facility. However, in-memory machine learning model took only 2 seconds on average. Moreover, when caching is used, it took only less than 1 second. As workers are created with multiple threads, machine learning models are designed as a class with a thread of safe singleton design pattern. The singleton design pattern is a software design pattern that enables an instance of a class used as a unique across multiple threads. The design pattern reduces the space complexity of the machine learning models from order n to order 1, when n is the number of threads. Figure 6 shows the proposed architecture of multi-thread single model. Or moreover, as the model is created in a thread-safe manner, there is no concern about multi-threading problems. In-memory machine learning model and the singleton patterns enables the system to make inferences as early as possible and to scale out concerning about increasing number of the thread and memory uses. The figure 6 is a multi-thread, multi-model, and multi-thread and single model. And figure 7 is the performance comparison of standalone system and distributed system. Distributed system. Distributed system also contribute to the scalability in the proposed system while handling and processing terabytes of simulation log data set. It takes a long time to get result. When the number of projects increases, the processing time will increase proportionally. To prevent this, the proposed system consists of distributed servers and databases. Spark, an open source for distributed processing, and MongoDB, an open source for distributed system, is used. Moreover, using multithreading and system maximized its performance. Figure 7 shows the comparison of data processing time in different types of systems: standalone and single-threaded system, standalone and multi-threaded system, and distributed and multi-threaded system. The distributed and multi-threading system reduced processing time remarkably. For this reason, the system can be scaled up easily even if the number of projects and datasets increases. Automated pipelines. Automated pipelines include pipeline from the data collection to test case prioritization and automatic regression. The proposed system, automated pipelines are implemented as a directed acyclic graph in Airflow. As we have already used automatic design verification system, these pipelines are appended at the end of verification flow, generating logs. When test cases are generated logs, the proposed pipelines in this paper pick the logs and process data and run proposed prioritization algorithm. Finally, the algorithm overall recommends the optimal order of test cases. This flow works without any human intervention such as clustering manually, finding optimal primers for clustering algorithms, or reordering test cases based on domain knowledge. 5. Result. Chapter 5. Result. To validate the proposed test case prioritization algorithm and the system, hundreds of thousands of test cases were addressed from one of our verification projects. The dimension of components was reduced by 92% by using PCA dimensionality reduction algorithms. In clustering phase, K-means PCA algorithm K-means algorithm was chosen as it is suitable for our distributed system and showed better performance for our datasets compared to other clustering algorithms. In test case prioritization phase, five values were compared without TCP, random, farthest first, and closest first, and error count and runtime-wise algorithms. The evaluation was performed considering how early 90% of the errors were detected in the design verification process. In the original system, without TCP, total regression time was the longest with approximately 368 hours in Table 1, meaning regression was inefficiently done to detect different errors so far. On the contrary, based on the proposed algorithm, design verification time has been decreased when the test cases were prioritized after clusters by components. Of all algorithms, Farthest-First algorithm took the shortest verification time to achieve 90% of the error detection rate as shown in Figure 8. The number of test cases to find 90% of the errors also significantly decreases 23.9% with Farthest-First algorithm in Table 1. When comparing closest first algorithm and farthest first algorithm, it was observed that test cases in the farthest position of the centroid helped to find more different errors than the closest position. Before the experiment, error count runtime-wise algorithm was expected to have the best performance. However, the result turned out to be different. The possible reason for this result is that we compare different versions of the component. The number of errors and a runtime were changed across different versions. However, it is expected that this problem can be solved considering to the history of errors and components in the whole cycle of design verification. In sum, proposed algorithm shows reduced verification time with a least number of test cases. The proposed system is flexible and data-driven, and that it selects optimal the test case prioritization algorithm depending on the data sets. Figure 8. Comparison of test case prioritization TCP algorithms of clustering. Table 1. Time for detecting 90% errors of test cases prioritization algorithms. For weighted clustering, critical errors such as accessing registers were given weights. To evaluate the effect of the weighting, we compared the first occurrence of the specific errors. In weighted clustering, specific errors that are given weights were found in only 19 hours after starting regression, including simulation runtime, where the simple clustering algorithm took 45 hours to find the errors. According to the result, time and detecting 90% errors was delayed by up to 3 days compared to the simple clustering algorithm. Since the purpose of the weighted clustering is to find errors in the earlier stage, there is trade-off between the detecting different errors to finding specific errors. Therefore, the proposed algorithm can be configurable depending on the on purposes. Figure 9. Comparison of test case prioritization algorithms of weighted clustering. 6. Conclusion. In the design verification, it is almost impossible to review terabytes of simulation logs and debug errors one by one. This paper proposes a test case prioritization algorithm based on the clustering. The proposed prioritization algorithm finds different errors or important errors as early as possible. The clustering algorithm uses components as features of the test cases, such as tasks, functions, and errors. After clustering, test cases are prioritized, and each cluster considers weights of the components or how early the algorithm reaches a specific rate of error detection. We also propose robust and scalable system architecture handling terabytes of the data for practical use in design verification industry. The proposed system is configurable, and that weights can be given depending on the purpose, and the appropriate prioritization algorithm is selected depending on data. All pipelines run automatically without human intervention. To validate the proposed algorithm and system, hundreds of thousands test cases were used as data sets, compared to the conventional system without any pro, any prioritization. The proposed prioritization algorithms were shows a remarkable decrease in the design verification time. This indicates that the algorithm and system enable verification engineers to help to reduce repetitive and tedious debugging tasks and to focus on finding different critical errors in digital design. Even if the proposed algorithm showed improvement in debugging process, there still are many challenges. First, it is possible the name of the component can be updated even if there is no change in actions, and this may reduce correlation accuracy between clustering, result, and test cases. Instead of considering the literal meaning of the component, the context, such as functions, should be considered to solve this challenge. Second, this paper uses only K-means clustering algorithms and is suitable for our data sets. Our other clustering algorithm can be used in the future algorithms. Finally, the algorithm is based on a specific version of the project, but it can be improved by considering overall history of the project. Such challenges are under consideration in our future works. Okay, thank you for your time. See you next time.